Hello everybody, Root Beer here, and we are on our penultimate question for the 2015 Manitoba Math Contest. That's right, it's question number 9. So let's have a look here. Let A, B, C be vertices of an equilateral triangle, with D an interior point, such that the lengths AD, BD, CD are 3, 4, and 5. Immediately I'm thinking somewhere a right angle triangle maybe, although their lengths connected up to an interior point, so maybe some reflections or rotations might produce a right angle triangle, or maybe the 3, 4, 5 is a coincidence. Anyway, these lengths are 3, 4, and 5 respectively, and they're asking us for the area of the triangle. So let's draw a picture of what is going on here. So that's equilateral-ish. And then we got D in here. It doesn't really matter who's the 3, the 4, and the 5. By rotation and reflection, we can, and renaming things, we can make it however we want. Okay, so we got 3, 4, and 5 here. There's the point D here. And we want the area. Okay. So how could we get the area? So I'm thinking two ways to get the area. One, we drop some perpendiculars down here. And then I suspect using some trig, like the sine laws, we could get the area of each of these triangles, you know, ADB, ADC, or DBC, and add them all up and maybe get the area that way. But it is an equilateral triangle, so if instead I call the side length something like S, I know, and I think I did this on an earlier contest, or earlier question on this contest, but an equilateral triangle with side length S has area root 3 S squared all over 4, and you can prove that with some trig. So I think either way, trig is sort of the way to go. But if we can now we've changed the problem. We can either find the area, or we could just find this length S. Now, how can we do either of those? So, the 3, 4, and the 5, it's a toss-up as to whether or not the 3, 4, 5, just, you know, they picked 3, 4, and 5, or is it 3, 4, and 5 because we've got a right angle triangle somewhere? Now, these ones don't connect up to make a triangle, but we can do things, because it's an equilateral triangle, and this does happen with equilateral triangles. I've had some questions with squares or isosceles right angle triangles that do this. If we sort of rotate things, maybe we can get a right angle triangle. So I'll show you what I mean. I'm not seeing this working right now in my head, but maybe if I try and explain the technique to you guys, it'll pop out. So we have this triangle here, and it's got the 3 and the 5 and the 4. But if I were to sort of rotate it by 60 degrees, C stays where it is, A moves to what I would call A prime, B moves to what I would call B prime, which is of course just A. And here's B down here. But look at these lengths. So suddenly I've got 4 here, we got 5 here, and I've got 3 here. 3, 4, this area, this right here is 60 degrees, so that means this is a 5, which means this is a right angle. So I do have a 3, 4, 5 triangle. The only question is this useful? So I do get a right angle there. I just, maybe this is just a coincidence here, but get 5 there, 4 there. Can we use this to get an area in some way? I mean, that's the real issue, is how do we get the area? So the fact that the rotation did manage to give me something, and I could probably get the same sort of thing rotating other ways as well. So how about we draw a big equilateral triangle, and we will do this rotation several times. Put a 5 here, 4 here, and a 3 here. And now we will rotate once over here. That gets me a 4, a 3, and a 5. 60 degrees in here for the rotation, which means that this is a 5, and that means this is a right angle. But we could have rotated the other way by 60 degrees. So now this 4 length is 60 degrees away from where it was. So this is 4 here. And we got a 3, and this is 5. So this down here is a right angle. This one's 3. And we'll make it red, because the other one was green. I try and use my colors equally. So rotating... so I rotated that way. I rotated that way. Can't do a rotation down there. I'll tell you what, we'll make the blue one a rotation. So the problem is I rotated once clockwise and once counterclockwise. This is a problem when it's the 60-degree triangle. You can very easily get some overlap. So this time we'll rotate the 4 down. Here's the 5. Here's the 3. This has got to be 4, which means this is a right angle. This is 60 degrees here. We'll go back to the blue. So we'll rotate the blue one this way. So that's a 3. That's a 4. That's a 5. And this is an isosceles triangle. Actually, was I too hasty? No, because 5, 5, yeah, and 60 degrees. It's going to have to be by cosine law. And so now this is a right angle. But I feel like I've just made a giant picture of meaninglessness. What, if anything, is there to do? Well, let's see here. Here's an equilateral triangle. Here's an equilateral triangle, and here's an equilateral triangle, and I know how to get their areas because of this side length is 5. Okay, and now here's a right angle, here's a right angle, and here's a right angle triangle. I can get their areas 1/2 base times height. So I do have contained my smaller triangle. The problem here is I've got these extra bits, which I will highlight in green. So these extra copies but if I look carefully, this one here is just this one here. So I've sort of unfolded. Yeah, so let's draw a picture again, make it clear, because I'm sort of scribbling all over everything. Okay, so we make a triangle. Rotation is, I guess, not exactly what we need to do. We sort of are unfolding things, which is another technique, but I didn't think of it because it doesn't come up a whole lot. So we put this down here as a 5. No. This is 3, and this is 4. And this is 60 degrees, so this angle is the same as this angle. So we haven't exactly unfolded, but now the green triangles are the same area. Similarly, we can sort of put a triangle out here by 60 degrees. This is 5. This will be 4. This is 5 here. And now the purple triangles are the same. And we can do the same thing with red triangles. Because of the 60 degrees, that means that this angle here is the same as this angle here. And similarly, this angle will be the same as this angle because it's a full 60 degrees to go here. And this will be a 3, and this will be a 5. Okay, so by rotating, I guess, because we do need to explain what we're doing. We can't just throw a picture on there and call it a day. So by rotating, what are we? We got A, B, and C, and D. By rotating triangles ADC, we'll say CDB. I'm just trying to keep some order here. CDB and BDA, 60 degrees about. So I rotated ADC by 60 degrees about A, C, and B respectively. We get the following figure, which has twice the area of our equilateral triangle. So maybe I don't need the side length. Maybe I don't need AC, or maybe there's another way to do this question where we specifically talk about those side lengths. My first instinct with those side lengths S that I put in there was cosine law, but I don't think that's going to work out. I don't think, maybe there's a way to do cosine law. I mean, we do know some of the angles, like 60 degrees, but we don't know the angles at, like, we don't know ADC, we don't know ADB, so I don't think cosine law is a particularly viable strategy. On the other hand, this rotation thing, rotation does not come up a whole lot. I remember there was a Euclid a couple years ago when there was a really slick answer to it with rotation. And so rotation is something to keep in mind with equilateral triangles because they rotate nicely by 60 degrees. Isosceles right angle triangles was the one that happened in the Euclid. Hexagons are good to rotate because they're basically just groups of equilateral triangles. Squares can sometimes be rotated, but and they're nice because you don't have to rotate them fully by 90 degrees. You just rotate them by any amount, and then the 90-degree angle stays where it is. That can be quite useful. But rotation itself does not come up a whole lot. So there's probably this probably is not the intended way to do it, is what I'm saying. It's probably cosine law, some trig thing, I'm guessing. But it's nice to flex our rotation muscles. So this is twice the area of the equilateral triangle. Okay, but as I've mentioned, and I'm going to call this point C prime. This one here is B. No. Yes. No. This is A prime. And this has got to be B prime. Yeah, so I rotated CDB by C. Okay, yeah. Or about C. Okay. But A prime CD, B prime AD, and C prime BD are right angled. Well, no, I can't say that yet. I gotta point out that by cosine law, we see dA prime, dB prime, and dC prime have lengths 4, 5, and 3. Because BDA prime, CDB prime, and ADC prime are equilateral. So from there we can get the right angles. So ADB prime, BDC prime, and CDA prime are right angled. In fact, they're 3, 4, 5 triangles. So area of the figure is, and let's go back and make sure we have these right, ADB prime, yeah, that's the right angled one. So it's 3 right angled triangles. And then 3 equilateral triangles. So that's 3 of these plus root 3, 3 squared. So our equilateral triangle formula is coming into play. Okay, and therefore the area of the equilateral triangle, and I do like how rotation allowed me to not solve for the side length. So that'll be 1/2 that is 3 times 6, so 18, plus root 3 times 9 plus 16 plus 25, so 25 plus 25, so 50, over 4, all over 2, because it's half the area of the figure. And so that will be 9 plus the 2 and the 50, 25 will cancel. 9 plus 25 root 3 over 4, I guess. Yes? Okay. Yeah, so a weird looking area. The root 3 in there makes me think, maybe root 3 over 2. If we were going to use trig, I bet the 60 degrees and the sine of 60 degrees might play a role here. Then again, this 25 over, well, no, the 25 just because it's a 9 and a 16. I was going to say it might have something to do with the side length 5 triangle. Yeah, not a whole lot else to say. What is the S? Out of curiosity, what is the side length if we wanted to solve for it? So multiply by 4, we get 36 plus 25 root 3 is root 3 s squared. Okay. 36 root 3 plus 75 is 3s squared. Divide by 3 on both sides. 12 root 3 plus 25 is s squared. Oh boy. Okay. So that's going to be 3 squared plus 12 root 3 plus 4 squared. I mean, yes, that's true, but it's not going to be a helpful way to break that up. So I'm trying to write this as a squared plus 2ab plus 3b squared. So we'll have the root 3 there. A squared plus 3b squared is 25. 2ab is 12, so ab is 6. So I guess we'll have a quadratic. So b would have to be 6 over a, and so that would be a squared plus 3, 6 over a squared is 25. So we'll get a squared plus 108 over a squared is 25. So we get a squared, a to the 4 minus 25 a squared plus 108 is equal to 0. So a squared is 25 plus or minus square root of 625 minus 4ac, so that'd be 432. I don't like that number. All over 2. So 625 minus 432, 3. I need to carry a 1, so that'd be 5 and 12, so 9. 193. So a squared is 25 plus or minus square root of 193 over 2. I'm not going to get a good A out of that, and therefore I'm not going to get a good B out of that. So, yeah, solving for S would be quite a pain. Although I guess you only need S squared. So getting S squared from this is not so bad if you can get that somehow. But, yeah, okay. I'm glad I did it the rotation way. Out of curiosity, did anyone out there do this with cosine law? Because I'd very much like to know if there's a cosine law solution. I suppose I could look up their solutions. Because they would probably have... Well, they tend to list just one solution, not a whole bunch of alternates. So either they did it by cosine law or, maybe they did it by rotation. But I doubt that. Anyway, anyone out there, if you got a cosine law or really another way to do this, because I'm not satisfied that the rotation way to do it is sort of the intended way. I feel like rotations are very much either you get them or you don't, because they are not common. They're not common to do a rotation question. The only reason I even thought about that is because I had a 3, 4, and a 5, and I want so badly to make that a right-angled triangle, but they're not in the right places. And it happens to be equilateral, so you can rotate it. And yeah, we got the right-angled triangle that way. But actually, I suppose the 3, 4, 5 had really nothing to do with it, because so I know I answered the question quite a long time ago, but really, this rotation technique would work for it no matter what you had, because if we take really any lengths, maybe call them x, y, and z, rotating this, we get y, z. We'll still get z here. We'll still z, x. We'll still get x here. So yeah, I guess I lucked out, because the reason I did it was for the right-angled triangles, but it doesn't really seem to have mattered. Because as soon as I have these x, y's, and z's, here's equilateral triangles. So those aren't bad to do. Root 3 over 4, x squared plus y squared plus z squared. And then 3 copies of triangle with x, y, and z. But if we have Heron's formula, which some of you might know, some of you might not, Heron's formula would work out just fine. So we let S, typically we say S for semi-parameter, but I don't know, let's call it W is x plus y plus z over 2. So 2. Then this would be, so this area right here is square root of W times W minus X times W minus Y times W minus Z. So really, as long as I knew these 3 lengths on the inside, I can get the area of the equilateral triangle, period. That's pretty nifty. The 3, 4, 5 was, I guess, just a coincidence all along. Oh well, I think we've spent enough time on this question here. I think we have. We still have question 10 to go. So, I will see you guys for question number 10 in the next video. Have yourselves a wonderful day.